Hey everyone, in this video we're going to talk about how to integrate with partial fractions. Alright, so in this case here we have this integral of 3x to the fourth plus 1 over x squared minus 1 dx. And if we want to differentiate this, if we want to integrate this, we're going to have to use some partial fractions here. Notice that we can't just use substitution. If we made u equal to x squared minus 1, we take that derivative, we're going to get 2x, and at no point, up here do I see a 2x dx. So it would be very difficult to use substitution there. I don't want to use parts because it's not written as multiplication, so I don't really have it in that form of the integral of u dv. So really I got to come up with something else to do. If I'm going to use integration with partial fractions, what that means is I need to create something where the degree of the numerator is less than the degree of the denominator. Right now that's not the case. Okay, so in order for us to use partial fractions, the degree of the numerator must be less than the degree of the denominator. So I'm going to have to go ahead and kind of figure out how to pull some things out of this fraction before that's going to work. So essentially what I have here is I just have polynomial division, so I can go ahead and write this as polynomial long division. The first thing I'm going to do is say, all right, we have x squared minus 1 is being divided into 3x to the fourth plus 1. And I'm just leaving space there for those zero terms that are missing. And when we do polynomial long division, remember we do first term divided by first term, so I'm going to do 3x to the fourth divided by x squared. I'm going to go ahead up top and I'm going to write my x squared. We do x squared, so actually it would be 3x squared. I'm going to do 3x squared distributed back to the x squared minus 1, and that's going to give me 3x to the fourth minus 3x squared. And we want to subtract. So right here, if I did everything right, the first term should always cancel out. And my second term here, I basically have a 0, right, a 0x squared there, minus a negative 3x squared. So when we go ahead and subtract, that's just going to give me, if I'm subtracting a negative, a positive 3x squared, and I bring down the plus 1. Okay, then it all kind of starts all over again. I have this x squared, it goes into 3x squared 3 times, so I put up a plus 3 on top, distribute back. We're going to get 3x squared minus 3, and one more time we want to go ahead and subtract, and if we did everything right, the first term cancels and I have a 1 minus that negative 3, and so that's actually just going to become 4. So really I'm going to take this integral right here and I'm going to sort of rewrite it. So now I'm taking the integral of 3x squared plus 3 plus 4 over x squared minus 1. And all of this is being done with respect to x. And so I can actually split this up into 3 different integrals now. So let's go back up here where there's a little bit more room. And I'm just going to rewrite this as the integral of 3x squared dx plus the integral of 3 dx plus the integral of 4 over x squared minus 1. Now the first two here are actually quite simple. So this one here simply becomes x cubed. This one here is simply going to become plus 3x. Okay, I'm not going to worry about the plus c because I'll just put it at the end over here. But this guy here, this one is a little bit tricky. This is where I need to use some partial fractions. I do need the dx at the end of it though. So in order to take this differentiation, or take this integral here, we're going to have to use partial fractions, which means that I'm going to have to somehow split this up. And again, I think a lot of people try to go ahead and use u substitution. They try to say that, oh, I'm going to make this x squared minus 1, that's going to be u. So then du would be 2x dx. And again, that would mean that I have to include a 2x up here somewhere, and I can't do that. I can't just input a variable like that. All right, so substitution is not going to work, and again, it's not written as multiplication, which means that integration by parts is also not going to work. So we're going to have to split up this fraction so that we have linear denominators. Okay, so let's just say, right now we have plus this integral and we're going to want something, so it's a over our factor x minus 1 dx plus the integral of b over x plus 1 dx. All right, so the way we're going to kind of figure that out is we need to, again, separate that fraction. So let's just come over here for a second. We're going to say that we have x squared, oops, it's going to be 4, rather. So we have 4 over x squared minus 1 is equal to a over, we'll do x minus 1 plus some constant b over x plus 1. And what we're going to do is we're going to take both sides of this equation here and we're going to multiply by the common factor. The common factor here would be simply x minus 1 times x plus 1. And as we multiply that through, we're going to get 4 is equal to a times x plus 1 plus b times x minus 1. Okay, and what we can do now is we want to basically, we know that a and b are constants, so we want to solve for each constant. So we're going to say that, all right, well, if I want to cancel out this b term over here, I'm going to let x equal a positive 1. And so if x equals a positive 1, then I'm going to get 4 is equal to, 1 plus 1 is 2, 2a, which means that 2 is equal to a. If I want to solve for this b term over here, I'm going to have to cancel out the a, so I'm going to let x equal negative 1. And if that happens, then I'm going to get 4 is equal to a negative 2b, so I get a negative 2 equals b. All right, so now we can go ahead and we can plug these back into our integrals here, and we can go ahead and finish out our equation. So that means that I'm going to have x cubed plus 3x plus 2, I'm sorry, the integral of 2 over x minus 1 dx plus the integral of a negative 2 over x plus 1 dx. All right, so let's go ahead and take each of these integrals here. So you can go ahead and you can use the u substitution. You may be at the point now where you start to sort of understand the patterns here, but I know that I can take out my constant from each one. So let's start with that. So I'm going to get x cubed plus 3x plus 2 times the integral of 1 over x minus 1 dx. And then this is going to actually be a minus 2 over here times the integral of 1 over x plus 1 dx. Okay, so in both cases here, if I did use my u substitution, I would let u equal this x minus 1, and then du would just equal 1 dx. Over here, it would equal, u would equal my x plus 1, and then again, du would equal my 1 dx. So I'm just going to go ahead and skip right to the antiderivative here. So I'm going to get x cubed plus 3x plus 2 times, and this is just 1 over u, if you want to think of it that way. So that's going to be the natural log of the absolute value of x minus 1 minus 2 times the natural log of the absolute value of x plus 1. Okay, and then we have, again, this plus c all the way here at the end. And so what we can do, this can actually be simplified a little bit. Remember that if you have a coefficient in front of a logarithm, it can be written as an exponent. So if I go ahead and rewrite this, it's a little bit simpler. That gives us x cubed plus 3x plus natural log of the absolute value of x minus 1 squared minus natural log the absolute value of x plus 1 squared plus c. Okay, and if we keep going, again, we're subtracting these natural logarithms here, and if we subtract the natural logs, we can go ahead and divide them. All right, so this could be written as x cubed plus 3x plus the natural log. And again, here's where you can get a little bit creative. If I have x minus 1, it's the absolute value squared. Well, the absolute value doesn't really matter because no matter what, if I square it, it's going to be positive anyway. So I don't really need that x minus 1 anymore, or so the absolute value anymore. So I can say I'm going to get x minus 1 squared divided by, and the same thing is true here, right? I have subtraction, so I know I'm dividing, but I have this x plus 1 in an absolute value squared, and again, the absolute value doesn't really matter because once I square it, it becomes positive anyway. So this is just going to be x plus 1 squared plus c. All right, and so there really are several ways you could have written it. If you would rather have taken out the 2 and left the 2 as a coefficient, that's fine, but then you would have had to have left those absolute values, those numerators and denominators as absolute values. So again, you could have also written it as x cubed plus 3x, right? If you decided not to bring in those exponents, you decide to leave the 2's out, maybe just factor them out as a coefficient, we can leave it as plus 2 times natural log of the absolute value of x minus 1 over the absolute value of x plus 1 plus c. And those really are equivalent. In this one here, I leave them as absolute values, and the 2 is outside. If I brought the 2 in as an exponent, it would be the whole fraction getting squared. In this case here, that's exactly what I did, and that's what it looks like there. So, really both versions are correct. Either one would have been fine. Okay, so this is obviously a little bit of a complicated example of how to use partial fractions. You're not always going to have to start with the long division. You only need to use the long division when the degree of your numerator is greater than or equal to the degree of your denominator. Okay, if the degree of your denominator is bigger than your numerator, you do not need to use this long division here. You can just jump right into using the partial fractions like we did right here. Okay, and again, once you're using the partial fractions, all right, at this point over here, we're going to split it up. So we have, our 2 or 3 or 4, however many linear terms you need, usually not more than 3. Once we have that split up, we're just going to integrate each term individually, and at this point here, we end up with, you're going to start to see the pattern where it's just going to be 2 times natural log of the denominator here, or the numerator times the natural log of the denominator. All right. So I hope this video helps. It's one of those things that takes a little bit of practice, but good luck, and I'll see you in the next one.